Okay, it's recording. So let's just start. Yeah, is any questions if you want to discuss, or if you have, just feel free to ask anytime. And I'll also monitor the chat. So if there are any questions, I can. Right. So let's just continue from what we were discussing last time. So we managed to define while pairing, and we were about to give a proof of why those properties hold. So let's just revise a bit because the proof involved quite a few steps and it's good to recall what we were doing. So this is from previous time. If we have a curve, then we have a concept of divisor, we have a concept of principal divisors. And for elliptic curves, what was most important in while pairing construction was this particular observation, that if you want to, so given a divisor of degree 0, it's not necessary that it is principal, right? So principal divisors are basically divisors that come from functions by collecting their zeros and poles. So if it is principal divisor, it will have degree 0, but just because a divisor has degree 0, there is no guarantee that it is principal. And for elliptic curves, what is nice is, given a degree 0 divisor, to check whether it's principal, it just suffices to check whether the actual sum is 0 or not. So divisor is a formal sum. So we forget that it's a formal sum and we actually start adding the points like we add in elliptic curves. And if they turn out to be 0, then our divisor is actually principal, which is quite neat and quite elegant. And we use this quite a bit in our construction. So while pairing is, first of all, whatever field our curve is defined in, we choose an n which is co-prime to the characteristic, or in other words, the GCD is 1. And if characteristic A is 0, then this is no constraint. We can choose whatever n we wish. So while pairing is basically a function from e, en cross en to roots of unity. And we constructed this function by basically taking quotient of two things. So we take a function g with respect to q, and then we evaluate at x plus p, take its ratio, and that is supposed to be a root of unity. And how did we construct this function? Well, basically so just to give a nutshell, so we choose a point q in En, and so from the observation of elliptic curves, we know if we take a divisor like this, n times q minus n times identity, since q is n-torsion, it has to be principal. So there is a function whose divisor looks like this. That is our f, that is our starting point, the first step. And using this f, we construct g, or we constructed g rather. So g is basically a function whose divisor looks like this summation. So we take q prime plus r minus r, where r is varying in En. And q prime was chosen to be any point, such that when we add q prime to itself n number of times, we get q. So this was our g, and then, yeah. So the rest of the proof, the rest of the construction was basically showing that if we take this ratio, first of all, this does not depend on x, so this is constant in x. And this ratio will be some root of unity. And that only depends on choices of p and q, not on x. So there are some nice properties that while pairing satisfies, and today we'll show a proof of those. So the first property was that it's bilinear in both variables. So let me write it again so that it's, so proof of properties. So first is that it's bilinear in both variables. And what it means is that, so we understand linearity, right? So whenever we hear this word linearity, it translates, or roughly we think of preserving addition, right? That's what, or even linear maps that we study, it preserves addition. So that's what we understand intuitively. So bilinear is simply like it's a map in two variables, and with respect to both variables, it's linear. So we fix one of the variables and it is linear with respect to the other one. So that this is what it is. So En P1 plus P2 Q. So it must be En of P1 Q times En of P2 of Q. Now this addition becoming multiplication on the right hand side might be a bit might seem a bit odd at first, but it is perfectly natural, because remember, whenever we are in vector spaces or anything, vector spaces are groups with respect to addition, right? So this is basically group operation. So here we are adding on in elliptic curves, but this is now roots of unity, right? And roots of unity form a group with respect to multiplication. So that's why this addition becomes multiplication here. And same thing holds with respect to other variable also. P comma Q1 plus Q2 is simply En of P comma Q1 times En of P comma Q2. So let's see why this is true. And I'll show for one variable, and the other variable is not exactly similar, so I can't say it follows by similarity. But the proof is given in, so all this while pairing stuff. So reference, did I? No. So all this is actually in Silverman's book. While pairing. So the title of the book is Arithmetic of Elliptic Curves. And the section is, I think it's chapter 3. Yeah, it is chapter 3. While pairing. All the proofs are given in detail. So I'll demonstrate for first variable because it's easier with respect to first variable. And second variable, it's given in detail in textbook. So let's show. So we want to show that En of P1 plus P2Q is equal to this product. But the way we define this is a ratio of G's. And how was this? So our second variable is in a subscript and first variable goes in the argument, right? So this is just x plus P1 plus P2 divided by GQ of x. So here I'm going to do a small trick. I'm going to manipulate this ratio a bit so that I can use what I want to prove. So I'm going to multiply and divide this ratio by GQ of x plus P1, and I'm going to do the same thing here. Okay. So let me rearrange the terms a bit so that it's easier to visualize what I will say next. Now this ratio right here, this is basically because our while pairing, the way we constructed it doesn't really depend on value of x. So it doesn't matter if we scale, if we add something to x, right? Because that ratio is going to be constant. So this ratio in the red box, this is En of P1 comma Q. Not sorry, P1, P2, sorry. Because x plus P1, I can think of it as new x, and then I'm adding P2 to it. So this ratio is basically E and P2 of Q. And the second box is exactly how we defined En of P1, comma Q. So the addition basically splits like this. Oh, which is nice. Okay. So the second property is that this while pairing is alternating. And what that means is, so En of P comma P is equal to 1. So if both my arguments are, so if both the variables are equal, then it is just 1. And En of, if I switch them, they become inverses of each other. So En of P comma Q is not exactly equal to this, but they are equal up to taking inverses. It's not, they're not that far from each other. Okay, so first observation is that to show second property, it suffices to show that how was the equivalence between E and G defined? Is it explained in the book? You mean is E is the while pairing? So the equivalence between E and G, I'm assuming you're asking what's the connection. So it is given in detail in the book. We also discussed it in last class. So the while pairing is simply this. So En basically takes two torsion points, P and Q, and the output is a root of unity. And this root of unity is this ratio, GQ of x plus P divided by GQ of x. So how do we construct G and how do we construct F? We already discussed that in last class. I just gave a very quick recap in 5 minutes. So they basically come from choosing functions whose divisors are exactly what we want. Like that would be a nutshell. So yeah, so En depends on this choice of G, and it's right. Did I answer your question? Okay. Yeah. Right. So second property is that it's alternating. So En of P comma P is equal to 1, and if you switch variables, they are same up to inverses. So to show the second part, that if we switch the variables, we get inverses, it suffices to show first property. So it suffices to show that En of P comma P is equal to 1. And why is that? So the second one follows from this. So let's see this first. So suppose we manage to show that En of P comma P is equal to 1 for all torsion points, right? So that will tell us that En of P plus Q comma P plus Q is also equal to 1 for all PQ in n torsion. Okay. But now I'll use that it's linear in two variables, right? So I'll use that. So let me fix the first one. So this is equal to En of P plus Q comma P times En of P plus Q comma Q. Okay. And now I can further break it into two because the first one is getting added. So I can, so this one becomes product of P comma P and Q comma P. And this one is P comma Q and Q comma Q. But we are assuming that whenever two variables are equal, the values are just 1. So this becomes 1. So this is equal to 1. this is equal to 1. So we are left with En of q comma p times En of p comma q, which is equal to 1. So now that tells us that En of p comma q is basically multiplicative inverse of this. So second property follows from this. Uh, Second property follows from first property. So now we will show. So let us show that En of p comma p is equal to 1 for all. Okay. Let me just write q instead of it doesn't matter, but just to be just to make sure I don't goof up while writing it. Okay. Because G always has q in its subscript, so just to make sure. Okay. So let's do this. So En of q comma q is gq of x plus q divided by gq of x, and we want to show that this is 1 always. So now again the proof is like some sort of a tricky or a very clever construction of a function that will give us what we want. So the key to constructing that function is translation maps. So let's look at translation map. Translation map or translation function or translation morphism. They're different things. So this map is always defined with respect to a fixed point. So fix a point, any point. So this q is not exactly same. So I want to say any general point. So let me just choose a general. So tau s. S is any point on elliptic curve of Hs. This map is defined from E to E. And what it does is, so you take any point, it basically, so the name translation. So you just add S to it. That's the map. We start with a point on elliptic curve and we keep adding this point to it. So this is the translation map. So now let's look at divisor of a product I from 0 to n minus 1, where n, remember, n is something that we have fixed. These are the torsion points, and I'm defining well pairing on these torsion points. So this capital N is something that is fixed. F. F was what we started with in the previous lecture. So I'll just recall a bit what property F satisfies, but F is the function from previous class. Composed with this translation function. And what am I translating by? I'm translating it by I times Q. Okay, let's look at divisor of this. And just to recall, how was F chosen? F precisely satisfies the divisor of F is n times Q minus n times the identity point. This is how we chose our F. Okay. So this is a product, right? And like there are n terms, so it's complicated. So we can look at one at a time. And divisor of product of functions is sum of divisors, right? And that just follows from, because if I, so divisor of a function is nothing but collecting information about its poles and zeros, right? So if I multiply two functions, the zeros, so order of the zeros, they get added up, and so for poles, right? So if I multiply, so what I want to say is that if I take product of two functions, and if I want to look at divisor of the product, this is nothing but sum of divisors. Because the zeros behave, order of the zeros behave additively. So that's it. So instead of looking at this big product at first, let me start by looking at one term at least. So let's look at what is divisor of f of tau iq. So this composition, this is so this function is composition of f and tau. So it takes just a minute to see this, but if my f has 0 at a certain point, let's say f of x is 0, and then I want to ask what are the zeros of this composition. So I want y such that this is 0. But what is this exactly? This is f of iq plus y equal to 0. And I know all the zeros of f, they are basically x, right? So what is y? Y is nothing but x minus iq. So all the zeros, they get translated like this. And so will happen with the poles, right? So if we look at f, how we chose it, it has 0 at q. It has exactly 1 0 at q of order n. This is what divisor means. And then it has a pole at identity of order n. So zeros are getting scaled, right, by this relation. So this is exactly what the divisor look like. It will be, so n is going nowhere. So we have q minus iq minus minus iq. So I'm just using this sort of thing, this sort of information here. Mm. So I scale it up, or rather down. I'm subtracting, so I'm translating it by something. Okay, so this is divisor of one function, but I'm taking product, so I'll have to add the divisor. So this entire divisor of product, this is basically sum of all the things, and each one has n in them, so I can just take like n, this n out. So I'll have summation I from 0 n minus 1, and then I have 1 minus I times q minus. Actually, let me not write it like this. It seems a bit confusing. So let me just say q minus iq. So this is the point, and the coefficient is, because I've taken n out, so the coefficient in front of that is just 1 minus iq. Okay. Now, if you look at this sum, there are a lot of cancellations that are going to happen. And in the end, I'll only be left with identity. Let me let's try with small n so that it will become clear why do we have so many cancellations. So suppose our n is 3. Then what does this sum look like? It looks like 3. And then our I is going from 0 to 2. So when I is 0, I have q minus 0 times q. Well, 0 times q is simply identity, and q minus identity is q. So I have q, and the, and then minus again identity. So I'm simply have 0 minus identity. And now this is a divisor where, just to uh, again, just to clarify, inside the parentheses, these are the points. So this is my, so when I say minus I times q, I'm basically thinking of adding and then taking additive inverses. And then these plus and minus 1, these are the coefficients in my divisor. So we have to be careful of when we are adding an elliptic curve and when is this a formal sum. So when I is equal to 0, for example, I have q minus iq. Well, this is now elliptic, adding an elliptic curve. So 0 times a point is just identity, and q minus 0 will be q. So I have q with 1 as a coefficient. So that's the first term of my divisor. And now I look at the second term, I is 0. So I have identity and then minus. So this is my first divisor, q minus 0. Okay. Now the second divisor is when I is equal to 1. When I is equal to 1, I have q minus q. Q minus q is simply identity. So I have identity minus 1 times q. So minus 1 times q, or just minus q rather. Okay. And the third term in my divisor is when I is equal to 2. So I have q minus 2q, but q minus 2q is simply minus q. So minus q. Okay. And then minus I is equal to 2. So minus 2q. Okay. Let me just clarify everything. Q minus identity, when q is 1, I have identity. So no, this should be minus q. Okay. And because I have minus 1, right? So I'm taking minus q. Right. And then when I is equal to 2, I have minus q minus 2q. All right. So we already see some, and whenever we add divisors, we add them coefficient wise, right? So we have two identities and their coefficient are plus and minus 1. So this one cancels out with this. So I see a minus q here and a minus q here with plus and minus 1. So this cancels out. So I'm left with these 2 points. So what we do with this? So here is an observation, not an observation, just a bit of recall. What is q? So q is 3 torsion point, right? So 3 times q is equal to 0. So 2q is minus q, or minus 2q is q rather, right? So this divisor simplifies to q minus, well, q. But then look at the coefficient plus and minus 1, so it cancels out. So we are left with 0. So this was just to demonstrate how the cancellation works out. In general, this sort of thing will happen. We'll be left with nothing. We'll get 0 here. Edward identity is 0. Okay, so if divisor of a function is 0, basically it means that there are no poles and no zeros, right? So if a function has no zeros, no poles, it must mean it's a constant. So this product I from 0 and minus 1 f of tau iq is constant. Let me not use another variable. Let me just say it's some constant. It doesn't matter. All we care about is that it's constant. Right? Or in other words, it doesn't depend on x. It's a function with variable x, right? So it doesn't depend on x. So I can choose whatever x I feel will be lit. Anyway. So now, yeah. Now you must have realized why did we choose to chose to do things this way, why we took this big messy product, so that we can have enough cancellations and in the end we get 0. If we took only one term, we wouldn't have cancellations. So that's why, just to cancel everything out. Okay, so now we are almost there. So now let us choose a point q bar that satisfies n times q bar is equal to q. So I'm choosing this point. It can be same as what we did before. I just wanted to recall. I didn't want to say that we did it last time. It's just we, yeah. So q bar is our chosen point so that this condition is satisfied. And now let me look at this product. So product of G composed with tau I q bar to the power n. Now its composition with power n. So this will be basically product of, remember how, so G and F are basically same as last time. And so again, this is a bit of recall here that G to the power n was F. So this, when we raise it to power of n, we will get product of F composed with tau I q. Let me not use square. This is, I mean, I don't want to use extra notation. This is simply what I've been saying. We add it. And this product is simply over I from 0 to n minus 1, same as what we were doing. Okay. And we just showed that this is constant. So it implies, just so that it's clear, and this, sorry. Okay. So now something raised to the power n is constant. So that simply means that this product is also constant. It's some constant, it not really doesn't matter. Okay. So now this is, we are almost getting to the punchline, just one or two steps. So this is constant. It means it doesn't really depend on the value of x. So I can choose whatever value of x, and I'm about to exploit this in a second. So this product I0 n minus 1 g of tau I q bar of x is simply, so how the composition works. It's product I0 n minus 1 g of, well, tau of iq prime applied to x is simply you're adding iq prime to x. So this is it. And we just showed it's constant with respect to x, right? So I can choose a different value of x. So this must be same as product I is 0 from n minus 1. Instead of x, I take x plus q bar plus iq bar. Okay. And now if these two products are same, there must be some cancellations. There are a lot of cancellations actually. So just to just to write in a cleaner notation, this is x plus I plus 1 q bar. So you can see on both the sides we have products varying over I, but there bound to be a lot of cancellations. So after cancellations, we'll be left with exactly one term on left hand side and one term on right hand side. And that is, we'll be left with g of x, and on the other side we'll be left with g of x plus n times q bar. But a q prime was chosen strategically. N times q prime is, or q bar, whatever, it's exactly q. And this is what we had. This is what we wanted to show. We wanted to show that en of q comma q, which is nothing but this ratio. And this g, the way we define, there is always, it depends on q. So sometimes I write it, sometimes I forget to write it. I'm so sorry. I mean, there are too many notations to take care of, but this, I mean, just let me say that in red here. So G is same as writing GQ. The construction always, it depends on Q. So, okay. So this is that. And now we just showed it's equal. So it's one. Okay. And now we already saw that this implies that if we switch variables, then we get multiplicative inverses. So let me just take a, this was quite, not quite, I mean, it's methodical, but it's somewhat involved. So let me, any questions at this point? Let me just take a pause for maybe half a minute.
I've got a question,
Yeah,
but maybe it should wait till the end. I can see why if your field is finite, then it has non-zero characteristic. I
yeah.
can't see necessarily the reverse, that if a field has finite characteristic, then it must be, has non-zero characteristic, then it must be finite.
If a field has non-zero characteristic, then it must be finite. Okay, let's, I can answer that. Okay.
That's
So,
probably something simple I'm missing.
no, it's perfectly fine. It's, so here is a, let me write down. So just from, just if somebody is reading it later, so so question, I'll just say question from chat and I'm answering it. So the question is, if characteristic of K is non-zero, then why do we know that K is finite, right? That's the
Yeah,
question. Okay. So character, so remember how we define characteristic. Zero is really, so given any field, so let K be any field. This is more of a general idea. Or let me choose a different word because K is in the question. Let me say R. So let capital R be any field in the universe. So there are only two situations, right? Every field has one. So whatever is one of R, we can keep adding one to itself and we never stop. We never get zero.
mm,
So this is never zero. And the other situation is that you keep adding one to itself, and after a certain point, you do get zero, right? These two are the only choices, and
yeah,
mutually exclusive and exhaustive. So whenever we are in the first situation, we say characteristic is zero. And whenever we are in the second situation, we say m is the characteristic, whatever the smallest m is, right? For which this holds.
mm,
So now if characteristic is non-zero, so if characteristic is non-zero, that means that there exists an m smallest, let's say, such that m times 1 is equal to 0. Actually, while answering that, I realized this is not really true. So let me not, okay, yeah. Yeah, so whatever I said here, this is correct. This is correct. But yeah, that does not mean that K is finite. Yeah.
yeah, that's where I was stuck.
Yeah, so this is a correct statement. And here is an example. So here is an example. We can do this trickery. Let's take our coefficients to be in the finite field, F3, let's say. And let's collect all the polynomials in single variable. So this is polynomials in single variable with single variable x with coefficients in F3. Now we can add and we can multiply here, but we cannot really divide, right? So
Yeah,
this is not yet a field, but we can do this. We can take its quotient field. So quotient field. Or I don't remember if we discussed. I don't want to use jargons. This is basically what I'm doing. I'm taking quotients. So where f and g are in f3 of x and g is non-zero. So so this is similar of how we construct rational numbers from integers. Integers give us multiplication and addition, but we can't really divide in integers. So to make sense of that as a field, we go to rational numbers. And this is what I'm doing. I collected all the polynomials, but I can't really divide. I mean, if we divide two polynomials, that not necessarily a polynomial. So I'm taking all the quotients like this. Now this is a field, right? And this has characteristic 3 because all the coefficients are coming from f3. So if you take any polynomial, you take 3 times that, it's going to be 0. But it's not finite, it is infinite.
Ah, that's what I was thinking of.
Yeah. So this is infinite simply because we can look at all these polynomials 1, oops, 1 x square x cube. These are different polynomials because we only say two polynomials are equal if their degrees are equal and their coefficients are equal. So these are different degrees. So this is an infinite set contained in f3 of x, which is contained in this quotient that we constructed. But it has characteristic 3 because every polynomial, if you just take 3 times that, that will vanish. So yeah. So yeah, this is, yeah, just because a characteristic of a field is finite doesn't really mean that as a set K has to be finite. It can be infinite.
Okay, yeah, thank you.
Yeah.
Because the where I'm getting at is you need the finiteness to show that these finite fields are algebraically closed so that you can get these roots of unity.
Yeah. So here's the catch. If we start with a finite field, it need not contain all the nth roots of unity that I want.
Right.
N being the while pairing. But I can always go to an extension where it will be contained. And that will be my finite field. So
Oh, okay, thank you.
yeah, we can do that. That's perfectly fine.
Yeah, I hope that's not too much of a distraction.
Oh no, please, yeah, please feel free. Any questions anytime, just feel free. Okay, so the next thing, and these properties shouldn't take much time. This one was the lengthiest. So the third property that we want to show, that this pairing is actually non-degenerate. And this non-degenerate, like different books have different ways of expressing it. It, like if the function is nice, like it's a pairing or something, they all boil down to saying the same thing. So this is what the claim is. If if en of p comma q is equal to 1, and here I'm thinking of q fixed and I'm varying p. So if this is 1 for all p in en, so fixed q, this is only possible when q is 1, or q is identity rather. This implies q has to be the identity. And why is that? Because if this is equal to 1, that implies that this function gq of x plus p is equal to gq of x for all p. Okay. So there exists a function h such that g is basically h composed with this map n. And what is this map? So this I'm thinking of from e to e. It sends any point x to n times x. But if this is the case, their nth powers must also be same. But g to the power n is really just f. So this gives us that f is basically h to the power of n. Now, if I multiply, if functions, their divisors get added. So n times divisor of h is basically divisor of f. But our f was chosen that its divisor is n times q minus n times identity. So if that is the divisor, so that simply means that divisor of h is q minus o. And now this is a principal divisor. So this, if this has to be principal divisor, that implies that q has to be the identity. Because I forget that it's a formal sum and I actually start adding it. So I add q minus o, which is just q. It has to be identity. So q has to be. Fourth property is that it respects the Galois action. So it respects Galois action. What it means is, so here when I'm thinking of Galois, I'm basically thinking of, so if we take Galois group of k bar over k, let's take any sigma in it will act on roots of unities, right? This is simply because all the roots of unity are solutions of this. But this is defined over the base field, right? So if if I take any root of unity, I apply sigma to it, that's also a root of unity. So sigma acts on roots of unities. So if I want to understand what is sigma of p, sigma of q, what is the pairing of that, and sigma also acts on these torsion points, right? Because again, my elliptic curve is defined over base field. So this is this makes sense. That's what I want to say. And I want to understand how is this connected to En of p comma q that I started with. This must satisfy the obvious thing that it must be sigma of En of p. So this is basically g of sigma q of x plus sigma p divided by g of sigma q of x. Now, if I construct my function g with respect to sigma q of x, it's nothing but sigma acted on gq of x. So this is sigma of gq acted on x plus sigma p divided by sigma of gq of x. And now this is sigma acting on this ratio overall. So hmm, I'm just thinking, what am I? I'm missing something here. I'm not sure. Because this is sigma of En of sigma p comma q. I want to say it's actually equal to sigma of En of p comma q. I'm not sure if I missed something. So let me, yeah, let me not. ponder over this. Let me say, I'll correct it. I'll correct in next class. Sorry about that. I'm not sure what I'm missing. Maybe I did something wrong. I'll just look at it again and but yeah, I want to say that basically I want to say that if we take while pairing of sigma p comma sigma q, that same as taking en of p comma q and applying it by sigma. So this should be equal to sigma of en of p comma q. I'll just look at its proof again. So sorry about this. The last property is so let me just say if somebody is reading it has errors, please look at uh, lecture 9 notes, which will be next week. So I'll fix this anyway. Sorry. So the last property is that it's so there is some sort of compatibility between various ends. And what this property means is that, of course, I can also talk about while pairing with multiples, right? And there should be some connection between multiples. So this means that if I take a torsion point in E of n times n prime, and I take a, let's say, n torsion point, and I want to look at this while pairing instead, applied at s comma p. And by the way, because p is n torsion, it's also n prime torsion because it satisfies something stronger. This is simply taking en of n prime s and p. S is n prime torsion, so n prime s is n torsion, right? We are adding it. So okay. And why is this? All I have to do is look at divisor of f to the power n prime, and this is simply n prime q minus n prime of o. So again, points versus coefficients. So now G composed with this map, when I raise it to the power of n prime, this will simply become f composed with n prime raised to the power of n prime. So E n prime of any point s comma p, or let me just say p comma q, doesn't matter. Oh, I've used a different notation, so let me say s comma p. This is simply G composed with n prime of x plus p divided by G composed with n prime at x. And this is G applied at y plus n prime of s over gy. And this is nothing but En of n prime s applied at p. So what I'll do proof of 4 again, because I think I made some mistake while I was doing it, but I'll look at it again. I think it would be really helpful to just go over the proofs again in a textbook, just to go over various steps and see how everything is connected. Most of these things, the backbone is that we already started with two clever functions, and this is how we're just playing around with the devices essentially. So this is it anyway. So this is just a summary of previous two summary so far. Let me just say. So we have a pairing from En cross En to the roots of unity And the word pairing basically, because it satisfies all those properties, that it's bilinear, alternating, Galois equivariant, and compatible, and so on and so forth. So a map like this. And why this is useful? Remember how this story it all started, because we were trying to study how to attack certain problems, right? So let's go back to, we had this elliptic curve, discrete logarithm problems. So elliptic curve, discrete logarithm problem. The problem is, if I take 2 points, P and Q, and I know that Q is R times P, how do we find R? This was the problem. And now the advantage of this is that we can think of this problem from elliptic curves. Using this pairing, we can think of it as a problem in solving this UN, which is may not be easy depending on how large and how complicated our points and our field is really. But still, solving it over elliptic curves is definitely more intimidating than solving it UN. And when we are in UN, like the roots of unity, it's a multiplicative group. So we can use index calculus methods and everything to attack this problem at least. So the setting is, so this attack is MOV attack, I think named after its founders, at least it's Menezes, Okamoto, and Einstein. Right. So we have an elliptic curve, let's say, over a finite field. Let's say, so any finite field, there is always a base field, right? And we take powers. So let's say Q is P to the power R. And suppose we have 2 points of order N. P does not divide N. So this is really a special situation that I'm thinking it of. I'm not talking on how to attack this problem in generality, because I want to use while pairing, right? And while pairing makes sense when Rn is co-prime to the characteristic. So that's what I'm assuming. And suppose we know that Q is equal to R times P, but we don't know R. We have to find it. So now, how do we convert this? So the first step is to compute the cardinality of points of E, not over FQ, over which it is defined, but to go over some extensions of it and to compute its cardinality. Let's give this a name. Let's say this cardinality is C. And how will I choose K? When do I know when to stop? It should contain all the n torsion points, because just because my curve is defined over a field, let's say rationals for example, or FQ, just because my elliptic curve is defined over rationals doesn't mean I can find all the n torsion points there. I have to go to certain extension to find it. So this is my extension. I will stop uh, whenever I find all my n torsion points there. Okay, so now it contains all the n torsion points, and n torsion points form a subgroup, right? So this n must divide this C, because C is the size of the entire group. Okay. This is simply by Lagrange's theorem. So Lagrange's theorem is that order of a subgroup divides order of a group. That's what I'm using. And the second step is to choose a point T in this extended field such that T should not be defined over the field that I started with, and M times T should not be identity for any smaller M than C. Sorry, not M, C. So now once I have made this choice, I define a point like this, C over N of T. Because order of t is c, it's not smaller than c. So order of n, oh, sorry, order of s is simply n. Yeah. Because n times s is c times t, which is 0. And if I add s to itself for any smaller value than capital N, then it would mean that t has a smaller order than c, which I'm not choosing it like that. So now, last step is simply to observe that if I take En of p comma s, and if I raise it to the power of r, see, so because of its bilinear nature, this is simply rp of s, and this is simply q of s. Actually, doing this, now I've realized I don't need this extra condition because this is too strong. I don't want my order of s to be n. I simply want n times s to be 0. So this suffices. So I don't have to do this. No, I don't have to do this. So all I can do is I simply choose this and then I define my s like this, and I don't care whether order of s is n or not. It's okay because I know n times s is 0. But I have to be sure that s is not identity. So suppose s is identity, then what I can do is then I can go back to 2 and choose a different t. Sorry, choose a different t. Right. Okay. So now to find this r, basically I have to do so to find r, perform index calculus methods or any state of the art known techniques to solve discrete logarithm problem in this group of roots of unity. Now the advantage of while pairing is exactly like this converts elliptic curve discrete logarithm problem to solving discrete logarithm problem in a multiplicative group. And if our q or the base field that we started with is not too large, then index calculus methods provide quite a efficient way to solve this in UN. So there's one. I think I should stop. In next class, probably what we can do is we can start with just having a recap of some of these properties, and I'll give the proof of point 4 again because I think I goofed up somewhere. And then we can discuss Miller's algorithm, which exactly. So, in all this construction of while pairing, we basically said that if we start with a point, then we can choose our f and g such that certain conditions are satisfied. But what exactly are those functions and how do we compute them? We can see Miller's algorithm on how to find these functions explicitly. So I think that we'll discuss next week. So let me just end here. Oh, I just saw the chat. Okay, bye, Dimitri. It's okay. You can watch the recording. So let me stop recording at this point. If there are any questions, we can discuss.